which is Dr. Yuyan Zhu is a postdoc at Stanford University, and her research interests span the fields of medical image computing and computer vision and machine learning, and most importantly at their intersection. So let's welcome her to give the talk, and her talk is entitled Diagnose Like a Doctor, Integrating Domain Knowledge into Medical AI. So thank you.
Oh, yeah, let me try to share my screen. Can you see my screen now?
Perfect, thank you. Go ahead.
Thank you. And yeah, thank Professor for the introduction. Hi, everyone. Thank you so much for inviting me to talk at Medical Computer Vision Workshop at CVPR 2021. My name is Yun Zhou, and I am currently a postdoctoral research fellow at Stanford University. Today, I would like to talk about my recent research efforts on how to better disseminate the existing AI techniques by exploiting different types of domain knowledge. As we know, in traditional clinical workflows, the analysis of medical images must be handled by radiologists or doctors. Sometimes the results are also needed to be carefully checked by additional experts for the more challenging scenarios, which make this process time-consuming and costly. Therefore, AI for medical image computing has become a more popular alternative to deliver automated medical image analysis. AI algorithms can perform accurate segmentation, localization, classification, and many other tasks. These tasks are essential prerequisite for clinical quantitative assessment and also facilitate further treatment and surgical planning. With the recent success in AI, or more precisely in deep learning, we have witnessed time and time again that good AI systems can offer the potential to serve as a second reader to decrease the misses and also increase efficiency. And more importantly, AI-empowered medical image computing systems can also support better decision-making and treatment delivery in later stages. Despite the great progress achieved so far, only a small part of existing techniques have been successfully deployed into the real-world clinical scenarios. I have listed some of the key challenges here, like the complex contents in medical images, the small and sparse lesions, subtle texture changes of certain structures, multiple modalities faces, partial noisy annotations, various and diverse clinical environments, so on and so forth. Since medical images are more constrained and static than natural images, we hypothesize that the incorporation of domain knowledge prior should obtain more accurate, robust, and plausible results in the face of such challenges. And specifically, I will first introduce the structural prior from the perspective of network designing as well as learning strategies. And then I will go into the data prior, which arise from the data properties. And after that, I will touch on the pervasiveness of medical knowledge in real-world clinical applications. So let's go to the first part. Specifically, I will introduce two types of structural priors. The first one is called the cost-to-find learning paradigm, and the second is the self-attention-based methods. This design is motivated by human cognition hierarchy, where the global features are usually perceived more quickly than the local features. We choose this design since it also well aligns with how radiologists interpret medical images, especially for analyzing small targets. For instance, the radiologist would first go through the whole image before zooming into the local details to identify this particular lymph node. So to understand how global and local processing would differ in practice, we have run two sets of experiments, one with the whole images and the other one with the region of interest. We have evaluated both experimental settings on the public CT datasets, which consist of 82 healthy cases. We use four-fold cross-validation, and we find that the segmentation accuracy on all 82 patients is only 75.7 by training and testing on whole CT images. However, when conducting experiments on the same, using the same experimental setting, but only on the Oracle bounding boxes, we can easily get a performance boost of around 8% in terms of average dice. And by noticing the results, we can find that the segmentation outcome is usually much more refined, and also the noise false positives are reduced in the background region, which is why the performance can improve so significantly. And this brings us to my MICAI 2017 paper, which involves two training strategies named as the core stage corresponding to training on the whole CT images, and also the fine stage corresponding to training within the region of interest. In practice, since we don't have the ground truth oracle bounding boxes, the region of interest would be acquired by using the testing results from the coarse scale models. And now you may wonder, what if the testing or the localization results coming from the coarse scale model is not very accurate? Would that error propagate to the fine stage and result in further accumulated error? And to answer this question, we propose to use a fixed point model for stabilizing the prediction during the inference stage, which is an iterative optimization by updating the input as well as its corresponding segmentation output alternately. And we call this the fixed point model since the prediction appears in both the input and output end of this equation. And the intuition behind this is that if we already obtain a perfect segmentation mask for the current iteration, then we would anticipate there are no more changes for the updated input as well as the corresponding segmentation output for the next iteration, because the localization quality already reaches the best. Now coming back to the training pipeline, except for training in such a stepwise version, in my CVPR 2018 paper, we noted that our coarse-to-fine model can also be trained in an end-to-end fashion. And the key differentiator here is that we propose to use a saliency transformation module for converting the probability map from the coarse stage as the spatial ways to be applied upon the fine stage. And in practice, we will find that this end-to-end training paradigm would always yield more accurate results than a stepwise training. Besides finding the saliency region on the output space, we can also find it in the feature space. By using the self-attention block, we can directly identify salient regions in the feature space, therefore reducing the need for two-stage training. As for the application, in our recent paper, we have showed that a self-attention mechanism can largely benefit the trauma detection, which comes with variable contrast, intensity, and can be extremely small and scattered in pelvic CT. And our method is actually quite simple. Taking an existing network architecture, we simply throw a set of lower level features into a self-attention block and then concatenate the attentive features back to the output feature space of the original network to predicting the final outcome. We show a set of qualitative examples here where we can see that such a simple usage of self-attention mechanism not only can reduce the false positives in the background, but also can enable a more refined and smoother prediction. Except for using the self-attention block as a plugin to existing CNNs, we have also exploited self-attention as an independent architectural component, which gets rid of convolution layers once and for all. And this is achieved by using the transformer architecture. Based on this, we have recently proposed the first transformer-based medical image segmentation net framework in our recent work, TransUNet, which is not only able to encode strong global context by treating the image features as 1D sequences, but also well utilizes the low-level CNN features while a U-shaped hybrid architectural design for enabling precise localization. As a result, we have achieved far better results compared with many competitive CNN architectures for multi-organ segmentation. And we have also attempted to use transformers for tackling data heterogeneity in different federative learning pipeline. And this is our results. We show that using transformers, not only can we achieve a less performance degradation on non-heterogeneous data partitions, but also can enable a faster convergence, which is make them especially suitable for the communication efficient federative learning platforms. And that includes the structural priors, which are enforced by altering architectures as well as training strategies. And next, I will introduce the data priors, which arise from the data properties, including the size prior, the shape prior, and the spatial prior. So the first type of data prior that I want to talk about here is the size prior. What is the size prior? To illustrate this, I have shown the following 3D renderings of different abdominal organs, where the first row is sampled from the JHU internal data, and the second row is sampled from the MICAT 2015 Multi-LS Labeling Challenge. Despite that these images are collected under different scanner conditions, different imaging protocols, and different patient populations, we can still notice similarity of patient-wise abdominal organ size distribution, which defines the size prior here. So why do we need the size prior here? On the one hand, we believe that the use of size priors can mitigate the imaging differences from heterogeneous data sets, as previously mentioned. And on the other hand, we believe it can also help to handle imperfect annotations. So by imperfect annotations, in the real world, ideally, we would want more high quality, fully labeled data sets, as in this case. But in the real world data sets, they are usually scattered and disjointed data sets with only partial labels available. And we call this type of partial labeling as imperfect annotations here. So we would want to address such difficulties by using the size prior. And this brings us to my ICCV 2019 work called Prior Aware Neural Network for Partially Supervised Multi-Organ Segmentation. The key idea here is that the prior aware neural network assumes that the average organ size distribution in the abdomen should always approximate their empirical distributions, which is the prior statistics obtained from the fully labeled dataset. And to achieve this, we aim to minimize this following KL divergence loss between the two distributions of the known labels as well as the unknown labels. We refer to this loss term as the prior aware loss and propose to use it as a soft global constraint on the overall optimization. And consequently, this new loss can help us stabilize the training process and enable and enhance the segmentation results, especially in the face of partial labeling from non-standardized datasets. And the next data prior that I want to talk about is the shape prior. Specifically, I will introduce my CVPR 2020 paper, which uses the shape prior for improving the segmentation accuracy of tubular structures. Noticing that the tubular structures can be well represented by its skeleton and the cross-section radius. We propose to learn the distance transformation maps as an auxiliary task to embed such knowledge. Specifically, besides learning a standard segmentation network, we also learn the distance map in a multitask learning framework. The distance map is consisted of the distance transform value from each tubular structure voxel to the tubular structure surface. And during the inference stage, we would use this predicted distance to reconstruct the 3D outcome by using a geometric aware refinement module. And the empirical results also demonstrate that this method is particularly useful for segmenting the tubular structures like the pancreatic duct, blood vessels, etc. Besides using the size and the shape prior, I have also investigated the usage of spatial priors for different medical image segmentation problems. The spatial priors can be widely observed for various applications. For instance, in this case, we can see that the pancreatic cyst sits within the associated pancreas. And in this other case, we can see that the splenic injury resides near the splenic boundary. And there are more similar cases, such as the liver, as well as its associated lesion, the pancreas, as well as its associated tumor. And based on this observation, I propose to exploit the spatial priors as deep supervision. Besides using the system mask as the supervision, I introduced extra deep supervision from the pancreas into the segmentation network so that the cyst segmentation can be improved with the help of relatively easier pancreas segmentation. The spatial priors can also be exploited as self-supervision. In this other MICAI 2020 paper, we have shown that in multi-organ segmentation, we can formulate the spatial relationship by solving a jigsaw puzzle. That is to recover a CT scan from its shuffled patches. And this is our segmentation branch. And we use the jigsaw puzzle here as a proxy task to provide extra self-supervision and then jointly train it with the organ segmentation task. And interestingly, we find that this additional self-supervision does not bring too many benefits for standard fully supervised settings, but can be especially beneficial for domain adaptation between different institutional data. So after introducing the structural prior as well as the data prior, in the final part, I would like to take a step further and touch on the essential prevalence of medical knowledge for various clinical applications. And that is, we aim to integrate the domain knowledge based on different task specifics. So this is the first application that I want to talk about, is also overlapped with Professor Elliot Fishman's talk, that we aim to exploit the multi-phase information for PDAC segmentation. So PDAC segmentation is one of the most deadly pancreatic tumor. For better detection of PDAC mass, dual-phase pancreas protocol using contrast-enhanced CT imaging are usually recommended. And therefore, in the real clinical practice, radiologists would often refer to multi-phase images back and forth before making the final decision. To exploit this multi-phase knowledge, in my MICAI 2019 paper, we constructed a dual path network for handling the multi-phase data, where each path is intended for one phase exclusively. And to enable the information exchange between these different arterial and venous phases, we apply skip connections across different paths of the network, referred to as hyperconnections. Moreover, we also introduced an additional pairing loss term to encourage commonality between the high-level features across different phases to benefit the final fusion process. Now, this design is trying to mimic how the doctors are referring to both imaging phases back and forth before arriving at the final decision. And in my other recent MICA 2021 paper, we also developed the first pancreas segmentation model by using the patient phenotyping. Phenotyping here refers to interpretative underlying patient information along with the disease progression and treatment. And we can notice that different phenotypes correspond to different patient subgroups and the image feature patterns, because disease progression and treatment delivery are associated with different care trajectories, which would lead to varying patterns in patient imaging data. And we also want to show examples of 4 different phenotyping subgroups of variant pancreas features. And the first one is the healthy pancreas group with potential lung infections. The second group is the type 1 diabetes and other chronic kidney disease patients with atrophic pancreas. And the third group is the other metabolic syndromes, including type 2 diabetes. And the final group is the patients with weight loss and also pancreatitis. So we can see that each group has very distinct image patterns that corresponding to a certain phenotype, which based on this observation, we would hypothesize that the incorporation of such patient phenotyping knowledge will largely benefit the segmentation of the pancreas. And therefore, we have designed such an CT phenotyping embedding network to combine the image features as well as the predictive phenotyping to facilitate the final pancreas segmentation. And interestingly, we find that our learned phenotype embedding can also be used to test the normal pancreas segmentation as well. And our empirical results suggest that our method can improve normal pancreas segmentation as well. And this suggests that our method can have huge potential for a lot of other applications as well by using the phenotyping approach. And finally, we would like to bring up our 3 major takeaway messages to conclude today's talk. And the first one is that the medical knowledge is prevalent, and also it can arise from various sources like the imaging physics, statistical constraints, and task specifics. And second one is that medical knowledge can help learning with non-standardized data sets, mitigating data biases, facilitating knowledge transfer across clinical environments, and therefore can be very applicable for real-world applications. And third one is that we believe that integrating medical knowledge should lead to more variable, reliable, and practical AI solutions, and more research should be done along this direction. And that is all of my talk today. Thank you for your listening, and I'm happy to take questions in the later panel session. Thanks.